So now that we've discussed voltage and current, we need to discuss resistance and power before we can move on to discussing how to examine simple circuits. Resistance is exactly what it sounds like. It's the resistance of the current to flow through a circuit. Every material has some sort of resistance, some have more than others. For example, a copper wire will allow electrons to move much more easily than a sheet of glass would. This is due to the fact that their valence electrons can very easily transfer from one atom to the next. Whereas in glass, they are largely locked in place, and it's going to be a very, very slow flow of electrons. This property is known as their resistivity, and it is represented by the variable rho, or Greek letter rho. The resistivity for a material should be a constant and is usually provided for you when solving a problem, or can be looked up on your own if you're solving your own problems. Now, to look at the resistance of our copper wire, several factors are important to determine it. The first thing you need to do is take a cross-sectional area at any location. And when we take the cross-sectional area of a cylindrical wire, we are left with a circle. And now, if we're looking at the total resistance of that copper wire, it's equal to the resistivity of copper times the length of the section you are measuring divided by the cross-sectional area of the wire. Now, a couple things should stand out to this. First of all, resistivity is directly proportional to resistance. So if it's more resistive to flow, the wire is going to have more resistance. Additionally, length is also directly proportional to resistance. A longer wire means you're going to have more resistance. And area is inversely proportional to resistance. This means that the larger the wire, the easier it is to flow. Or rather, more area means less resistance for the wire. All three of these proportionalities should be relatively intuitive. Now we need to look at the units. The resistance is measured in ohms. It is represented by the Greek letter omega. Omega. We'll discuss more on what an omega is defined as once we get into Ohm's law in the next section. Now we need to discuss the last main term, power, or how efficiently work is done. And this is defined as the amount of work done divided by the amount of time it takes to do that work. In circuits, this is obviously no different, but a couple of things I want to point out. First of all, remember that the definition of work is the change in energy. And in this case, it's caused by the difference in electric potential, or voltage. So now we need to figure out how to calculate the power going through a circuit. The power is calculated the same way that Barry Bonds got his power for all those years, through an IV. And yes, I know what you're thinking. He used a needle, not an IV. I know, but it doesn't make the analogy work, so for now, you're going to have to deal with it. When we look at circuits, specifically a light bulb, the electrons flow through the circuit, through the light bulb, and come out the other side. To do that, they have to be pushed, and when they get pushed through, there is an amount of friction caused by the resistance, which causes work to be done, usually giving off energy in the form of heat. That drop of energy is the voltage, or rather the voltage drop over that component, in this case a light bulb. In this light bulb, let's assume that before it hits the light bulb, the electrons have, or rather the current, has an electrical potential of 10 volts, and after it goes through the bulb, using up some of the potential energy to get through the bulb, the current only has 4 volts of potential energy. Because the difference in potential energy is 6 volts, that bulb's potential drop is, or voltage drop, is equal to 6 volts. And let's say that we have 3 coulombs per second flowing through there, or rather 3 amps of current. To calculate power that this bulb consumes, it's equal to the current flowing through it times the potential difference from before and after the light bulb, or rather 3 amps times 6 volts is equal to 18. But what unit is it? That's correct. Watt is the unit. I hope you enjoyed this section on resistance and power, and this concludes our introduction on simple circuits. And we'll move on to the next section, which is applying Ohm's law to a simple circuit to calculate the voltage, current, resistance, and power for each component in the circuit. Thanks a lot and have a great day. Bye.